My name is Frank Wilhelm Mauch. I'm a theoretical physicist and I'm the director of the Institute for Quantum Computing Analytics at the Forschungszentrum Jülich. And my role in QSolid is that I'm the overall coordinator of the project, and my institute is also contributing to various aspects of the software stack. So as a community, we are currently learning to go from single research groups with one or two principal investigators to really working as a large team with shared responsibilities, with people with very different expertise. We are long away from the situation where one group can build a quantum computer alone. That on the one hand makes us stronger because we have true domain experts for all the technologies we need. That's not only the quantum technological part, that's also a lot of what we call enabling technologies, microwave technology, firmware, cooling and things like this. With this management work package, we need to make sure that all of these experts work together, that they clearly understand what is expected from them and when, that they clearly understand what are the specifications in a language that they can really use. We also, because this is still a research project, we are not a company, we need to look at all the risks. We need to look at, is something delayed? Is there a situation where we need to make a decision because we tried out more than one method? And that's the role of this management work package. It also includes talking to our sponsors, to the public, and working also with our big sponsor, which is the German taxpayer, to interact with them so we all know that we're on the same mission. So here we are looking at the technology that's immediately around the quantum processing unit. So this is technology that on the one hand touches the magical quantum part and the very sensitive quantum part, but that then connects it to the outside world where we want to make sure that we, for example, have the right input and output to the system. And that, for example, contains the measurement device with which we are reading out the result of the calculation. This measurement device is a piece of superconducting technology on its own. So it's made from elements which are very similar to the quantum elements, but it's made in a separate process. It is measuring so well that the laws of physics, the Heisenberg uncertainty principle, are actually limiting it. But this way it is connecting the quantum part to the outside user, and it's part of what is taking a quantum experiment and actually turning it into a computer people can work with. Well, the challenge is that we need to isolate the quantum processing unit very well. If we don't isolate it, it follows the laws of classical physics, like any macroscopic object of our everyday life is doing. But we cannot isolate it completely because otherwise we cannot read and write. So this is something you have to work with on a daily basis. For example, our quantum devices are operated at very low temperatures, much lower than the temperature of outer space. So we need to make sure that everything we do to the system does not heat the system up. One big challenge in an output system is that it is very complex. It contains a lot of elements on the circuit which all need to be working with very, very high precision. We have had an initial success that the first generation of a small measurement system, a so-called parametric amplifier, which is working essentially like the electric version of a children's swing, is already operational, and it's a device that one of our partners at KIT is delivering to many other partners, and that we also hope to commercialize in near future. It's not the final device we need, but it's something that gets us started. So the hardware stack for external access team, which is led by my colleague Rami Barens, is just starting their work because they are in charge of really delivering the final product. They are in charge of turning all the experiments, all the development into a real computer. That means that they will run one setup with the cooling, with the electronics, and with all of its sensitivities and all of its fragility 24/7. So external users, programmers, can use this essentially in the style of a cloud service. So this is basically the paradigm shift from experimental physics to computing. This means that the people who are operating this setup do actually not know what's running on there, because some external user may be solving a logistics problem or a theoretical chemistry problem. Their role is to keep the system healthy. This is a challenge because these external users will probably run applications there that are really demanding. It's a big challenge to make sure that this very fragile and early technology is working at a high performance all the time. So there's, for example, one question: can we really run it 24/7, or how often do we have to take it down to maintenance? So this work package will ultimately be what QSolid is delivering for the community, which is what, if you work and run your applications on a QSolid device, this is where actually this is all then really taking place in the lab. So the team of Work Package 7 receives all the tools from the other work packages, so they are just ramping up. So currently they are building this laboratory infrastructure that is available for use, which has to do with purchasing the cooling equipment, with building the electronic system and building it in a sustainable way that can also run this way. So currently, even though we are doing quantum physics, there is a lot of electrical installments, plumbing, working with pumps going on in order to create this infrastructure. So with QSolid, we finally have the opportunity to build a complete quantum computer in Germany. This takes us from the devices and components where we already have big expertise, but brings them together in a complete system. So that means that Germany is positioning itself very well in this international field, and it's contributing its strengths. For example, a big strength that we always have had in Germany: we are a fantastic nation of component makers, of people who are making tools and subsystems. But with this project, we can also create a full machine, and only then we will also be able to improve all of these subsystems. We see next to the big system already a lot of engineering innovation coming out of our projects. And this will also allow users, once we have machines, to work with quantum computing in all German technology. Why is this important? Is because some applications of quantum computers require high privacy and high confidentiality. So you really want to know where your data are being processed and who is the middleman, if any. When you're building a team because you are responding to a call for projects, the first project year has a lot to do with building capacity and building connections. We see that we had a good start off in this very difficult process. We have seen teams of people working together who haven't really worked together before. That is a good start. It's only the first lap in a very long race. But for example, I'm very happy that the true German quantum computing pioneers from IPHT are now working very close to bring their expertise in fabrication combined with the expertise in running large systems that already exists in the researchers of PGI 13. We see that our software partners are truly connecting to the hardware partners. We see that our engineering team that makes the wiring solution is starting to have first products. So we see in the first project year that it's a lot of work, but I'm happy with how we got out of the starting box, the proof of the project, and its potential success we will only see at the end.